Hello, class, and welcome to Chapter 11, Section 3. After this section, you guys will take the Chapter 11 test, which will be a written test that you can fill out and submit. I'll go ahead and jump right into Chapter 11, Section 3, Reactions in an Aqueous Solution. And just a reminder that we just have one more chapter to get through before the semester is over, and that will be Chapter 12. All right, so net ionic equations. We live in a water-based world. As you all know, more than 70% of Earth's surface is covered by water, and about 66% of the adult human body is water. The most important chemical reactions take place in water in an aqueous solution. So water is incredibly important for chemistry, and that's why this section is all about reactions in an aqueous solution. The reaction of aqueous solutions of silver nitrate and sodium chloride, for example, will form solid silver chloride and aqueous sodium nitrate. That is a double replacement reaction. And this is how we can show this reaction. Aqueous silver nitrate plus aqueous sodium chloride will form a solid sodium chloride and aqueous sodium nitrate. This is a double placement reaction. The equation does not show that, like most ionic compounds, the reactants and one of the products will dissociate or separate into cations and anions when they dissolve in water. When sodium chloride dissolves in water, it actually separates it into sodium ions and into chloride ions. And when dissolved in water, silver nitrate dissociates into silver ions. You can use these ions to write a complete ionic equation, which is an equation that shows dissolved ionic compounds as dissociated free ions. So we can kind of separate everything else into the silver, the nitrate, the sodium, and the chloride. We'll form the solid silver chloride. We'll keep that together, but we're only going to separate out the aqueous solution ions. Notice that the nitrate ion and the sodium ion will appear unchanged on both sides of the equation, and then the equation can be simplified by eliminating these ions because they don't participate in the reaction. So for example, we'll write the net ionic equation. We'll separate every ionic compound into its component parts, and then we're going to eliminate the ions that will not participate in the equation. An ion that appears on both sides of an equation and is not directly involved in the reaction is called a spectator ion. And when you rewrite an equation, leaving out the spectator ions, you have the net ionic equation. So we separated all the ions out, and we're going to separate or eliminate the ions not directly involved in the reaction. Those are called spectator ions. That's what the red X is going through right now. And then the net ionic equation will be an equation for the reaction in the solution that shows only those particles that are directly involved in the chemical change. So we've written out our chemical equation. We separate out the ions. We're crossing off the ions that do not participate. Those are called the spectator ions. And we get the final net ionic equation, the equation that shows only those particles that are directly involved in the chemical change. In writing balanced net ionic equations, you must make sure that the ionic charge is always balanced, and the net ionic charge on each side of the equation is 0 and is therefore balanced. Consider the skeleton equation for the reaction of lead with silver nitrate, for example. We take solid lead plus silver nitrate in an aqueous solution it will yield silver solid and lead nitrate in aqueous solution. The nitrate ion will be the spectator ion in this reaction. And the net ionic equation is as follows. Silver plus lead, so solid lead plus aqueous silver will yield solid silver and aqueous lead. This is an unbalanced equation. Why is this equation unbalanced? Because notice that a single unit of positive charge is on the reactant side of the equation, and 2 units of positive charge are on the product side. So this is unbalanced. In order to balance it, we'll add a 2 in front of the silver on both sides so that the charges will balance. So now we'll have 2 positively charged on this side and 2 plus on the right side. And that ionic equation shows only those particles involved in the reaction and will be balanced with respect to both mass and charge. And of the 5 types of reactions identified in this chapter, both single and double replacement reactions can be written as net ionic equations. So let's go through a sample problem. We'll write and balance a net ionic equation in this sample problem. Aqueous solutions of iron chloride, iron 3 chloride, and potassium hydroxide are mixed, so they're both aqueous. A precipitate, that means a solid of iron 3 hydroxide forms. Identify the spectator ions and write a balanced net ionic equation for this reaction. Precipitate, let's see what that is. It usually means a solid, but it might be a solid within an aqueous solution here. So let's identify the relative concepts. We'll write the complete ionic equation first. We'll eliminate aqueous ions that appear on both sides of the reactants and products, and then we'll balance the equation with respect to both mass and charge. All right, so we'll write the complete reaction, including the states of matter. So we have iron chloride aqueous plus potassium hydroxide aqueous will yield the solid precipitate iron 3 hydroxide and potassium chloride aqueous. Let's apply the concepts to this solution. We'll first balance the reaction. So we want to make sure the number of atoms on the product side equals the number of atoms on the reactant side. And we'll write the complete net ionic equation for the reaction, showing all soluble ionic compounds as individual ions. So we first balance, and then we separate everything out, as shown here. Iron 3 aqueous, 3 chloride aqueous, 3 potassium, 3 hydroxide will yield iron hydroxide. Remember, we never separate out the solid, the precipitate, but we will separate out everything in the aqueous solutions. Now we eliminate aqueous ions that appear as both reactants and products. So let's eliminate those chlorides, let's eliminate those potassium, because those then will be the spectator ions. So what are we left with then? We balance the net ionic equation. So we're left with this, and we want to make sure everything balanced includes the charges. So this is balanced because the 3 positive ions will balance out the 3 negative ions. So the charges will balance on both sides of the equation. Predicting the formation of a precipitate. So sometimes when you mix solutions of 2 ionic compounds, an insoluble salt called a precipitate can form. In some combinations of solutions produce precipitates, while others do not. So whether or not a precipitate forms depends upon the solubility of the new compounds that form. By using the general rules of solubility of ionic compounds, you can predict the formation of the precipitate. So we use these solubility rules for ionic compounds. And I would encourage you to reference this chart when you're doing things like your homework. So will a precipitate form when aqueous solutions of sodium, what is this? I'm trying to think of the name. Sodium carbon oxide aqueous and barium nitrate aqueous are mixed. Let's see if a precipitate will form. Let's look at our solubility rules. We'll separate everything out by their ionic components. When these 2 solutions are mixed, the cations could change partners. That's sodium and that barium. Will a precipitate form? When we separate everything out, we changed around the cations, and we're going to see if one of these is a solid precipitate. Will a precipitate form? Refer to the solubilities rules to determine if a precipitate will form. Nitrates are soluble, meaning they will dissolve in a solution, so no precipitate will form in the nitrate. Carbonates are insoluble, so a precipitate will form with that carbon. So when we get the sodium nitrate, we know that's an aqueous solution, but we know the carbonate will form a solid because the carbonates are insoluble in a solution. So combined with barium, that will turn into a solid. So now, since we know a precipitate forms, we can write the net ionic equation for that reaction. So we're going to separate everything out, eliminate the aqueous ions, Those are the spectator ions, and we're left with barium plus carbonate will equal barium carbonate. One more sample problem. Aqueous potassium carbonate will react with aqueous strontium nitrate. Identify the precipitate formed and write the net ionic equation for this reaction. We'll write the reactants, look at possible new pairings of cation and anions that give an insoluble substance. We'll eliminate spectator ions. So let's write the reactants showing each as dissociated free ions. We can switch the cations and use the solubility rules to determine new insoluble substances. So we've switched the cations around. We know that nitrates are always soluble and carbonates are always insoluble. So we know that a precipitate will form. We'll separate everything out into its components. We'll eliminate the spectator ions, and then we'll be left with our balanced equation with the two aqueous ions equaling the solid precipitate, because we know the carbonate ion will be a solid. Lots of information in that section. Let me know if you guys have any questions. A great way to study this is to read through the textbook and work through a lot of those practice problems in the textbook as well. Thanks for listening, everybody.